In this video, I'd like to look at a simulation of rolling dice until one rolls a snake eyes, 2 ones, and sort of do several samples of that, and then sort of do a little analysis of the results. Okay, and obviously I'm in Wolfram Cloud or Mathematica. So if you had it on the desktop, I'd call it Mathematica. If I'm up in the cloud, I call it Wolfram Cloud. Okay. Here we go. It's sort of the whole simulation for the most part is here in this one line, though a very complicated line. And I've spread the one quote unquote line over many lines. Okay. So it's one input anyway. So at first I'm establishing a list, empty to start with, of where I'm going to put my results. So that is this snake eyes equals curly bracket, semicolon. Okay, then I'm establishing a for loop using the for method. The for method has 4 arguments. With the for loop, you are typically, you know that you're going to be counting something. That's the normal use of a for loop. And so I'm going to be counting. My counting variable is I. The first argument of the for method is to initialize the counter, just to decide where you're going to start counting. I'm going to start counting at 1. The second argument is the condition under which you will continue to count. So I will continue to count so long as I is less than or equal to 100. And then the third argument is what I am incrementing by. I++ is the shortcut for incrementing by 1. So you could just as well say I equals I plus 1. Okay, then the fourth argument in the for method is the statement you want to perform iteratively, the what you want to repeat. Okay, and so then I have a number of statements I want to repeat. The first statement I want to repeat is I'm going to have a counting variable. I want to count the number of rolls it took me to get snake eyes. So for each sample, I'm resetting that counter back to 0. So that was this line here, count equals 0. And then the next thing I'm doing is I'm going to continually to roll my simulated dice until I get a 2, a snake eyes, or I'll say so long as I don't get 2. So I'm not doing it until, I'm doing a while. So while the simulated dice are not equal to 2, I'm going to continue. So this is my while loop. A for had 4, Mathematica handles for loops as a for method with 4 arguments. And currently we're somewhere in the middle of the 4th argument of our for loop. A while loop is handled by a while method, which has 2 arguments, 1 condition and 1 a statement you want to repeat, statement or statements. In this case, it is just 1 statement. So here's our condition. So I have a nested loop. I have a while inside a for. My condition is I have random choice, square bracket, 1, semicolon, semicolon, 6, close square bracket, plus another version of the same thing. This is a simulated rolling of a die. So I'm getting randomly or pseudo-randomly, if you want, a random number between 1 and 6 inclusive. I'm adding a second one. So this is 1 die, this is 2 die. I'm adding the results of the die. So I'm summing the die values. And so long as that's not equal to 2, I do want to point out that I cannot type greater than or equal to sign like this. I typed greater than and then equal, and then it got sort of reformulated as this within Mathematica. And same thing here for the not equals. I typed an exclamation equal, and then it got sort of reformatted as this not equal sign. But that was not something I typed. This was not something I typed. Okay, but so the while loop, the while method has two arguments. The first, a condition. The second, a statement or set of statements. In this case, it's just a single statement of incrementing the counter. When the while loop is finished, then I am taking my count and adding it to my list. So I'm going to have a list of how many times it took me to get snake eyes. And then when my fourth is the end of my for loop here, this square bracket is the end of my for loop, I am just printing out the number of snake eyes. So this was, right now, this is not entered in this current instantiation of this notebook. This is a previous result, but if I come here and hit Shift Enter, I will get sort of a new set. So this is a new set now, starting with 15.1. And I can get different samples. Okay, so I got 100 samples, not much, so my statistics won't be great. This is a sort of a loop within a loop. So if you make, and this inner loop can sometimes runs. So we see here 101. So it's 106. So it's possible. It's got a very long tail. Yeah, there's a 1. So there's usually sometimes you get it on the first roll, or you can roll it hundreds of times and not get a snake eyes. So it's a distribution with a very long tail, as we'll see in a minute. Okay, so I'm going to perform, this is a previous histogram of a previous result, but let's Shift Enter and get the current histogram, and you can see that it's got this distribution has a very long tail. And then you can just get some of the standard measures. I'm going to get the mean. Wolfram Cloud Mathematica likes to do things very exactly, so it would, without the n, it would give me a fraction, like a huge denominator over a huge numerator over a huge denominator. Wasn't really interested in some exact value. It's just a sample after all. So I put the n around it to get it to evaluate numerically, and I decided how many digits of precision I wanted. Okay, you can, this number will change. It will come more of the sort of, theoretical results as you get increase your number of samples. So the average number of times it takes to roll in this case was 31.54. I believe like a theoretical answer would be 36. The standard deviation tells us some information about the spread of these things. See that it has a very long tail, that it is very spread out. So we get a very big standard deviation. I've seen bigger standard deviations for other samples. So this particular sample is not as spread out as usual. Other measures, it's clearly not a normal distribution. It doesn't have a peak with tails on both sides. So it is definitely skewed. Let's enter that. And we see here the sort of craziness that you get in Mathematica, because it assumes an audience who wants a very exact answer, which does just for some simulation result doesn't seem very useful, but we can get numerical value. So the skewness, it's pretty skewed, not surprisingly. And the kurtosis is a measure of how it falls off. Sort of, this is it symmetric around the peak, which it's not, and then this is how does it fall off. And I think a normal distribution, we tend to compare things to normal distributions, would be a 3, and this is a 4.62. So not normal, very spread out. Okay, that's what I want to show you. Just sort of play around with some sort of programming, some simulating. In Mathematica, we have a list to collect our results. We had a for loop. We had a while loop within the for loop. Took me a little while to get used to this notation, but understand that the for loop and the while loop are methods. So you have arguments separated by commas. Once you this is sort of different than most programming languages, but if you understand it as a function or a method, then this notation with the commas begins to make more sense to you. Or at least that's what made it make more sense to me. All right, that's what I wanted to show you. Thanks much for your attention.